All right. Well, welcome back, folks. Let's go ahead and let's pick up where we left off with yesterday. And we were talking about volatility, and I had described for you volatility as being the rate at which a particular liquid will evaporate. The faster the liquid evaporates, the more volatile it is. And so volatility is basically related to the evaporation of a liquid. Okay, so we can imagine then that a liquid that evaporates faster at a certain temperature will be more volatile. The volatility is related also to reactivity, if we want to consider that. The more volatile a liquid is, let me take that back. The reactivity can be related to the volatility, but reactivity, remember, depends on what else interacts with the particular compound. But we see then, for example, gasoline. We always refer to gasoline as being a very volatile liquid. Now, the reason for that is that it generates a very high vapor pressure at a given temperature, room temperature. And if there's a spark around, it will react immediately with the oxygen in the air. The volatile liquids tend to have a very high vapor pressure, and as such, then if they interact, and they do tend to interact, they tend to be very combustible. And so when they interact with oxygen and they have that little bit of spark, then you get a pretty good reaction. Okay, so the same thing holds true for dimethyl ether. That's also a very volatile compound. Hexane is a very volatile compound. So compounds that tend to have a high vapor pressure combust for the most part very easily. So they tend to be fairly reactive in that sense. Okay. And so what I did was I asked you yesterday then to consider then four different compounds here. Okay, four different compounds. And I asked you, of these four, which one would have the greatest vapor pressure? Okay, so let's go ahead and consider that here. So we are going to describe then the information. We're going to look at the information given to us on another pressure temperature graph. Okay, so this pressure temperature graph where we see that, and we're comparing four liquids here, four compounds. Okay, dimethyl ether, benzene, water, and phenol. Okay. All right. So the question is, of these four, which one would have the greatest vapor pressure? Okay. Now remember, vapor pressure, we said yesterday, and what we were talking about the day before was that vapor pressure is the pressure that forms above a liquid as a result of evaporation. And we were able to analyze a pressure temperature graph, and we were able to see two unknown liquids, and we saw then the liquid then that had the highest vapor pressure at a given temperature, at any given temperature, will then will then evaporate the fastest. Okay, so if we take a look at these here, so we take a look at, and it would have the greatest vapor pressure. Okay, all right. So let's go ahead and let's consider what we have here. So the question is, which one has the greatest vapor pressure? Okay. Well, let's consider the vapor pressure. Let's consider dimethyl ether first. Okay. So initially here, way down here at negative, let's say about negative 80 degrees Celsius. Okay, so negative 80 degrees Celsius, the pressure, and so again, the pressure is in torr, and this is a measure of the vapor pressure of this particular liquid. So at about, let's say about negative, and we'll call this about negative 90 degrees. Okay, so at about negative 90 degrees, okay, so negative 90 degrees Celsius, the pressure for dimethyl ether, and I'm sorry, let me go ahead and write it up here so we can follow where it's going. Okay, so let's go ahead and let me write it up here. So at negative 90 degrees Celsius, okay, the vapor pressure is what, probably about what, 20, less than 10, 20 torr. Okay, so that's at negative 20, that's at negative 90 degrees Celsius. Okay? All right, so going on to the next point, let's go ahead, let's take a look at negative 50 here. We'll call this negative 50. So about negative 50 degrees. So at about negative 50 degrees Celsius, the pressure now has climbed up to 200 torr. Okay, and then going all the way to, let's say, yeah, so let's go ahead all the way to about, let's say about negative 25 degrees Celsius here. Okay, so negative, if we trace this down right here, so we'll call this negative 25 degrees Celsius. At negative 25 degrees Celsius, the the pressure then is going to be about what 727 yes, about 750 torr. Okay, the 750 torr at about negative 25 degrees Celsius. Okay? So let's go ahead and do the same thing for benzene. Okay, let's go ahead and do the same thing for benzene. At negative 90 degrees Celsius, at negative 90 degrees Celsius, what is the pressure for benzene? Well, folks, look, it doesn't even register a pressure at negative 90 degrees Celsius. Okay? So that means then here, if you trace this line back, actually it stops right here, but if you trace this curve all the way back, it doesn't even register. So there is no pressure that is registered at negative 90 degrees Celsius for benzene. Let's continue on. Okay. What is the vapor pressure of water? And let's just stick with negative 90 degrees Celsius. What is the vapor pressure for water at negative 90 degrees Celsius? Same thing here. Look at this. If you try to extend this back, I mean, if anything, you would see that it may even sit below. It doesn't. You can't get below zero pressure. But we can say then that it also does not register a pressure at negative 90 degrees Celsius. And going on here, folks, with phenol at negative 90 degrees Celsius, okay, it also does not register anything. There is no vapor pressure. None of the other liquids at negative 90 degrees Celsius even registers a pressure. Well, what do you think that means? That means then at negative 90 degrees Celsius, okay, there is no vapor pressure. There is no pressure that the liquid exerts. Actually, let's think about this. When does, for example, and I can ask you this because you won't know this for benzene and phenol, but I can ask you this. At negative 90 degrees Celsius, what state is water in? Water is not even in the liquid state at negative 90 degrees Celsius. Neither is benzene, neither is phenol. So none of these three compounds here are even in the liquid state, let alone, so they're in the solid state. So there is no way that they can exert a vapor pressure if they're not in the liquid state. So with that said, the question then is, which one of these would have the greatest pressure? Well, we haven't gotten there yet. Okay, we can answer that now. At any temperature below negative 25 degrees Celsius, dimethyl ether will have the greatest vapor pressure. Because look at this, at negative 90 degrees Celsius, it's already registering 20 torr, okay? And it's all the way up to 750 torr at negative 25 degrees Celsius before any of these even start to exert a vapor pressure. Okay? Now look at this. Benzene doesn't exert a vapor pressure, so benzene doesn't exert a vapor pressure until about negative 15. At negative 15 degrees Celsius, it exerts a vapor pressure about 20 torr. Okay, and take a look at this. For water doesn't even exert that same pressure. So let's say about this is about what, about 3 degrees Celsius. At 3 degrees Celsius, it starts to exert a vapor pressure of 20 torr. And then finally here, okay, here at what, 70 degrees Celsius, that's when phenol exerts a pressure of 20 torr. So the temperature here, you have to increase the temperature here in order to get to this same pressure. So if we compare the temperature at which this pressure is obtained, okay, so they exert this is the same pressure here, but dimethyl ether exerts that pressure at a lower temperature, at a lower heat energy rate, okay, which means then at any temperature, and we can pick any temperature above below 25 degrees Celsius, dimethyl ether exerts the highest vapor pressure, okay, and so therefore dimethyl ether then is the most volatile of the 4 liquids, okay. Which one do you think would be the least volatile? Well, if you take a look at this, phenol then would be the least volatile because it doesn't evaporate very quickly. It doesn't evaporate very well, okay? So with that said, then we can use then these vapor pressures here to determine then the volatility of a liquid, okay? So the liquid that evaporates the fastest at a given temperature, it evaporates the most, is the most volatile, because the volatility is related to the tendency of a liquid to evaporate, okay? Which means then We take a look at this, which means then it is also related to vapor pressure. So volatility is also related to the vapor pressure. So the higher the vapor pressure, let's go ahead and do this here. The higher the vapor pressure at a given temperature, the higher vapor pressure at a given temperature. Okay, so at a given temperature, the more volatile the liquid. Okay, so that's what we need to be able to do. We need to be able to make that link between volatility and vapor pressure. Okay, so keep that in mind, and I think that'll help us as we move forward. Okay, very good. Let's continue on then, and so we talked about vapor pressure. We talked about evaporation. We talked about the those two properties of liquids. So vapor pressure and evaporation are properties of liquids. Gases don't evaporate. Gases don't exert a vapor pressure. Okay, solids do not evaporate, and they do not exert a vapor pressure. Okay? I'm sorry. Let me take that back. Gases can't, certain solids can exert a vapor pressure when it undergoes sublimation. Let's talk about that at another time. We'll get to that in the chapter when we get to the chapter on heat energy. Okay. All right. So with that said, though, at this point, the evaporation and vapor pressure are properties of liquids, and the volatility. Then we can, because volatility is linked to vapor pressure, we can say then that vapor pressure volatility is also a property that different liquids have as well. Okay, so let's talk about one last property of liquids, okay, and that is the ability of liquids to boil. Okay, so let me ask you this. So I wanted you to take just about a minute or so to answer this question. So make sure you write down your answer here and supporting a couple of sentences to support your answer. Okay. We talked about evaporation as a process of vaporization, liquid becoming a gas. We also mentioned then that boiling is a process by which liquid gets converted to a gas. And yet, I had mentioned then that boiling and evaporation are not the same. So what's the difference between the two? Take about 1 minute, answer the question about, and then let's get back together and let's talk about it. Okay, so go ahead, write down your answer. Okay, so boiling and evaporation, both are considered, okay, both are considered vapor processes by which liquids vaporize. Okay? All right, so we said then that with evaporation, let's talk about this first. Evaporation occurs when particles at the surface of the liquid, absorbs enough heat energy, so this is heat energy, absorbs enough heat energy where they start to move faster, okay, and faster. And some of these particles move, they'll have enough energy where they can move fast enough and they can break the attractions that they have for all of the particles around them. And so when they leave, they become part of the gaseous state. They leave up, they fly up into the space above the liquid. They fly up there. And so as soon as they break free of those attractions, then now if this was if it started out as a liquid particle, okay, now it has become a gas particle. So the transition from liquid to gas, that is a process by which we refer to as vaporization. But when that process occurs at the surface of the liquid, that's when we refer to that process as evaporation. Okay, so what's going on down here then with boiling? What's going on with boiling here that makes it different from evaporation? Okay, well, first of all, make sure you understand this. To get to the boiling point of a liquid, to get it to boil, we have to heat. Okay, we have to heat up the liquid. Now we said then, as you heat up the liquid, all the particles will start to move faster. Okay, so as the particles absorb more and more heat, they start to move faster and faster. Okay, so the kinetic energy increases. So as you heat up a liquid, the kinetic energy of the particles increase, their speed increases, and so at the surface of the liquid, the particles start to leave faster. And we said then that if you apply heat to a liquid, it's going to evaporate faster. Think again of the pot of water in the refrigerator versus the pot of water in Death Valley in the desert. Okay, all right. But what if we continue to heat it? What if we continue to heat and add more heat? We don't stop at however hot it is out in Death Valley in the summer, 115, 120 degrees Fahrenheit. Okay. So what if you continue to heat it to the boiling point? Let's say you heat it to about 212 degrees Fahrenheit, which is roughly the boiling point of water in Fahrenheit. Okay. What if you keep increasing the temperature of that liquid? Okay. So if you continue to increase the temperature of that liquid, make sure you understand then, as the liquid particles absorb the energy, okay, all the particles start to increase more kinetic energy. As you start to heat up the liquid more, remember the average kinetic energy of all the particles shift also towards higher and higher kinetic energies. And so with that said then, if all of the particles, more and more of the particles, not just the ones at the surface, start to increase their kinetic energy, what we get then, and let's go ahead and do this here, is the phenomenon known as boiling. Okay? And so what happens here is then, as you start heating up a liquid, it's not only the particles at the surface that increase their kinetic energy. Now we have all the particles, okay, all the particles in liquid start to obtain enough kinetic energy, liquid particles throughout the liquid obtain enough kinetic energy to vaporize, which means then, that means then, not only particles at the surface here, not only particles at the surface are starting to break free of their interactions, but we have particles down here at the underneath the surface, okay, that are moving so fast, okay, that they actually are no longer, and if you take a look at this, they are no longer attracted to the particles around this. So all these particles are attracted to each other, okay? So that's what happens here. They are attracted to each other. However, and let's go ahead and continue this here. So you can imagine then these are all the water particles that surround this one here. Let me change the color of this one, okay, to highlight it. Okay, let me go ahead and erase this one really quickly. Okay, so we have this water particle here sitting in the middle of all these other ones. Okay, it is moving so fast now. Okay, it is no longer attracted to any of the particles around it. And so, like we said, what's the main key feature that differentiates the liquid particles from the gas particles at the microscopic level? The attractions that they have, the interactions that they have with all the particles around them. So therefore, if you have this particular gas particle here, this liquid particle here, if it's broken, all of its attractions for the particles around it, it now has become a gas particle. It's become a gas particle underneath the surface. And so what do we see when we get to the boiling point? What is it that we observe? We observe bubbles. And what are those bubbles but gas particles that are formed under the surface of the water? And then they bubble up. They bubble up to the surface. And so when you boil water, folks, that's not air bubbles that are coming up. Initially, they're not. They could be air bubbles, air trapped underneath the surface of the water, and then on the sides you'll see that. But when you get that boiling water where the bubbles coming up from the bottom, okay, those bubbles are water vapors. They're not gas. They're not air bubbles, folks. They are water vapors that's appearing from the bottom of the water. Okay, and so what's the difference between boiling and evaporation? Well, first of all, when you boil, you get evaporation. Because so if you're getting particles underneath the surface to move faster and then they vaporize, well, you can only imagine then that the particles at the surface are also still acquiring enough energy, speeding up, and they are leaving. So when you boil a liquid, you're still getting evaporation. However, what you're also doing is that you're vaporizing liquid particles underneath the surface as well. And that's the key difference between boiling and evaporation. Okay? In boiling, evaporation, you only get vaporization at the surface. In boiling, you get vaporization throughout the liquid itself, at the surface and underneath the surface as well. And that's why we can observe that the observable event for boiling is the bubbles that form. Okay. All right. Very good. So let's go ahead then, and let me ask you. Okay. So how we will define boiling, and I'm running a little low on time here, folks. So how we will define boiling then is that we will define boiling in a more technical way. But first of all, make sure you remember, make sure you understand where we came from and what I'm going to give you now. What the difference is between boiling and evaporation. Boiling is the process by which vaporization occurs throughout the liquid. Okay, by increasing the temperature up to that point. Okay, so as you boil, you have to heat it up, and at some point you're going to see the bubbles in the liquid. Okay? All right. So we're going to define it, and we'll pick up with this discussion on Monday. We'll define then the boiling point then as the temperature at which the vapor pressure of the liquid is equal to the external pressure. That's a whole lot to try to take in at this point. Okay. And so what we're going to do then is so we're going to take this discussion here. Now that we can describe boiling at both the macroscopic, we see the bubbles, and the microscopic level, particles are absorbing enough kinetic energy throughout the liquid to break free of their attractions and thus become gas particles. That's the microscopic explanation. Now that we have made that link between what we can observe macroscopically and how we are describing the particle behavior microscopically, let's get a little bit more detailed in our discussion of boiling. And what we're going to do on Monday is that we're going to make the link between vapor pressure and boiling. Okay, so we want to be able to do that as well, and then we'll be able to finish up our discussion on liquids. Okay? And then we'll move on to discussions on solids. Okay. All right. So what I'd like you to do is over the weekend, I've assigned you set B from chapter 13. So please make sure you give those problems a try. Do as many as you can. I think you can do most of them, and then we'll finish up this discussion of boiling and liquids on Monday, and we'll start solids on Monday as well. Okay. All right, folks. Well, have a good weekend, and I will meet you back here on Monday. Okay. Have a good day.